Welcome back to System Software. So today we're wrapping up the main content of the course. Next Tuesday will be the final review. It will be recorded. We are going to have class and everything, even though it is the week, but it's a one class, so it's a tiny part of your grade if you have to miss it, or just let me know if you have excused absence. We're going to be finishing up with a classic attack on software that has led to lots and lots of exploitation of software called stack smashing. And it's a great example of an attack because it's based on the knowledge about how compilers work to implement functions, which we just learned about in this class. So you'll actually see how an attacker can exploit how compilers manage memory to do some nefarious stuff with other people's programs. All right, but before we begin, questions from last time. So last time we went over, it was supposed to be project review. We mostly went over CodeGen 3. I did an overview of how functions get implemented by the compiler. Questions on CodeGen? Or any projects in the class? Questions on any material, since this is basically the last class of main content before the final review. All right. So yeah, CodeGen 2 was due last time. Was that graded? Did you get grades for that? You should have gotten CodeGen 1. No CodeGen 1? Really? Okay, those should be out today. Apologies for that. All right, so let's go over the last homework 25. So this one probably came out a little out of left field and may have seemed unrelated to what you learned in the course. But the question was, what can happen if the return address stored by the calling function, if an array stored on the stack gets overwritten well past its bounds? Yeah.
The return address can be overwritten with what was only the wrong return address?
Yeah, that's right. So to illustrate what I was asking about this is if you remember our stack, we have a stack in memory. And what does the stack frame look like for a function? Well, we've got a pointer, the base pointer, which points to the old base pointer. That's the calling function's base pointer. Before that in the stack is the return address. Before that are, the seventh parameter, the eighth parameter, etc. And then we have our local variables here. So let's say we've got an array here, the variable x here. So this is our stack frame, right? This is during runtime when your program executes, the instructions that you generated to emulate functions, they're going to set up the stack like this. The calling function is going to push the parameters. It's going to then execute the call instruction, which pushes the return address. And then our prologue is what we saw last time. Our prologue will push RBP onto the stack and then update RBP so that RBP is now pointing to our stack frame, and it'll allocate space for the local variables on the stack. So that's what our generated code does to memory when your function is actually called at runtime. Questions on that? Questions on that part? This is a stack frame we just learned about, and then hopefully you're all implementing code, translation that will generate code that will do this. So we didn't talk about arrays, but how are arrays stored in memory in C, in C-like languages? What's the difference between an array and a scalar? A primitive data typed variable. Yeah.
Doesn't an array take up multiple memory cells?
Yeah, it takes up multiple slots in memory. It's a way of, if you have a variable like x, it can only hold a single value at any one time. If you have an array, like array, you can hold multiple values of the same type. So if x is an int, and we have an int array, if int is 64 bits, which, what's the question?
I'm not sure if this is outside the scope of the class, but I know specifically in Java, just because what I'm familiar with, that integers and longs, for example, have very specific numbers of bytes that are allocated to them.
Yep.
Why wouldn't it make sense, if we're planning on only using the integer 3, why does it make sense to allocate the remaining bytes to the integer if we would only be using 1 byte instead of, if we go above that 1 byte, then allocate another byte?
That's a good question. So why would you use an integer which takes up 32 bits when you only need a couple bits of it? And technically, you don't have to. So if you could write a compiler that could look at what data is being used by that variable, and you observe that it's only using a few bits, you don't have to allocate 64 bits for it. The problem is that it's difficult in general to figure out exactly what values variables will take at runtime. So for instance, they could be read from the user. They could be doing some complicated calculation, like calculating pi out to 1,000 digits. And it may be really difficult for a compiler to predict, first of all, that it is calculating pi and what those digits are. So in some sense, the purpose of the type system, or one of the uses of the type system, is so that the compiler doesn't have to know. The compiler can just look at what the developer asked for and just allocate whatever the developer asked for. But it's certainly the case that you, as the developer, could optimize memory usage by using a short instead of an int, if you know it's never going to exceed that. Or you could write a compiler optimization that can try to figure that out automatically. In general, it's impossible to do that. This is like the famous Turing halting problem, and Rice's theorem. It's impossible to know for certain program behaviors in general using a compiler. But you can do this in special cases. So if we see that x is assigned to 3 and it's never assigned again, then, we don't even need memory for that. We can always just use immediate values for that. So this is the subject of compiler optimization. We talk about it in compiler construction a little bit more, but it is a good point. Part of it is around ease of compiling. Even when you're writing an assembly program, you have to make a decision when you're writing the assembly program about how much space to use. And that depends on knowing what values you're going to have, the range of values for the whole program. And that can be tricky to do, yeah.
So another question, is there ever going to be a case where having too much memory is going to be a problem for the compiler? Like when computers were first coming out, we didn't have nearly as much memory in them as we do now. So is there ever going to be a case where having 32 or 64 or 128 gigabytes of memory could cause an issue for the compiler or the running program?
So the question is, can you ever have too much memory for a compiler? I mean, for compiler writers, you love having lots of memory, and programmers, you love having lots of memory. I don't see how it would be an issue. I mean, using too much memory in your program can make things slower because you have other programs contending for that memory. And so they have to write out, this is an OS class stuff, but the way modern devices above, like microcontrollers, manage memory is that programs can allocate as much as they want, but some of that memory may be copied to disk if you're requesting more than 8 gigs of data. So if you have like an application that's playing a movie, and that's like a 60 gig movie, it can't hold all that in physical RAM at once. So even if the programmer asked the machine to do that, the machine is going to say, okay, yes, but under the hood, it's really going to move that data to disk. Or it's just going to say out of memory, you've exceeded memory. But for the compiler is just translating languages. So the compiler doesn't actually care about how the programmer asks for memory. So the compiler is not responsible for performing the actual memory allocation. It just generates instructions that will request memory, like pushing onto the stack or making a call to the system to ask for more memory from the system. But if you're doing like embedded coding or low like microprocessor coding, you may want a compiler that optimizes for memory usage, and that includes the memory usage of the assembly instructions themselves. So, for instance, if you have a loop from 1 to 100, the compiler doesn't have to generate a branch for that. It could just copy the loop 100 times. That would be more efficient because branching tends to be slower than straight line code because architectures can optimize for it better. But if you're on a microcontroller with very limited space, you may prefer branching. Even though it may be slower, it uses less space because you have fewer instructions. So remember, all those instructions are stored in memory as well. Anyway, there are like sort of lots of engineering trade-offs between running time, space, what device you're running on, whether it's like an high-performance cluster or a tiny microcontroller. These are the engineering decisions, so that when you all go out to the career field, and depending on what application you're working on, what systems you're working on, these are all trade-offs. There's no like one answer that memory is always better than running time. On our kind of conventional devices, memory tends to be cheaper than like processing time. So we can trade off lots and lots of memory for processing time because it's cheaper on these devices. Small devices, that may not be the case. Okay, but interesting. So a little aside on memory allocation. So back to the problem here. So we didn't talk about it in this class. You didn't have to compile it in this class. But if you remember from programming in C, if we have an array in C, that array can hold multiple integer-sized values. So x, whenever you reassign it, you lose the old value, it overwrites it. But with an array, we can hold multiple values at the same time. It's like a list or a vector in math or abstract data types. So how does that work under the hood? The way C and C-like languages do it is that they arrange these values in contiguous memory. So for instance, if I have offset 0, array, remember, what is the value of this variable? If I just print out this value, this ARR variable, what am I going to get when I print that out in C? Did you guys learn this in like Intro to C? Yeah, exactly. It's the address. So if I don't index into the array, this ARR variable, this array variable, it's really just a pointer. So it's really just a pointer to the first value. So it's going to print out this address here, this address in memory. That's what's going to get print out. When I start indexing into it, array 0, what address does that have? Same address as ARR array, right? So this is array 0. This is array 1. This is array 2. These are ugly arrows, but I think you all should have learned this in C, right? Intro to C. So this is how an array gets laid out into memory. It's just the size of this data type times however many elements you want in that array. So if we assign array 0 to 2, this is what's going to get assigned. This location is going to get assigned. If we assign array 2 to 1, we're going to assign this memory location. If we assign x to 3, this memory location is going to be assigned. Make sense? So this is how, for local variables, for local arrays, this is how we lay them out. This is how the compiler will lay them out in memory. But notice a problem here. We've asked for a, oops, I made a mistake here. So we asked for a size 1, 2, 3 array here. But what happens if we write to index 0, 1, 2, 3, 4? If we write to index 4 and we set that to 0 or something, what's going to happen in this scheme? So first of all, does the C compiler allow you to do this? The C compiler does actually allow you to do this. And the reason is for the same reason as to why we can't always guarantee that we use a smaller amount of space for int. Because let's say this is array y. array y equals 0. And let's say we read y from input. We ask the user to give us what array index. Well, how is the compiler going to know whether this is out of bounds or not? The compiler can't know. You can't know at compile time because it could be any value. Now you could warn the user. You could say, look, this value is not a constant. This could be bad. You could warn them, and modern C compilers will warn you. But what happens if the user gives us 5, or 4 rather? What happens if the user gives us 4 and 7, or sorry, oh my God, y evaluates to 4 at runtime? What's going to be overwritten here? So this is array 0, this is array 1, this is array 2, this is array 3, that's offset 3. This is offset 4 in that array. So without any other protections or any other special checks, the compiler will just generate, and most C compilers will generate code that will just write to this address. And so what's going to happen if we write to that address? What's going to happen after we finish this function? Is it going to go back to the calling function? No, because we've lost the return address. This was our link to getting back to the calling function. It's no longer going to be a function call anymore. It's going to jump to some other address. Here it's going to jump to 0, and that's probably not going to be any executable instructions, but the processor will start trying to execute code at address 0 or whatever address you give it, because this is the return address. When you call the ret opcode, it just pops whatever this value is and branches to it. So in this scheme, if this indeed is coming from user input, well, now the user can potentially control where your program starts running. And if we can cause it to jump to attacker-controlled code, well, now your program is not just, setting some values or doing whatever task you wrote it to do. Now your program is just a general purpose program executor that any attacker can pass code to and have it run on your machine. So this is called the stack smashing attack. It's a classic exploit for software. Lots of software is vulnerable because most C compilers would just happily compile out of bounds array accesses because it's very hard to know whether it's out of bounds. And lots of code was vulnerable for many years, for many decades. And this was the source of a lot of remote code execution, where an attacker can just send a specially crafted request to like a web server or something, because a web server is really just a C program that's reading input and running a C code. And attackers could actually just run arbitrary code on a remote server, including, for instance, running a shell. And then you get basically SSH like you do in the Eustace, but on some random web server on the internet. All right, questions about this, the kind of reason why this happens? Or any thoughts on why a C compiler would do this? Or is there any mitigations to like not do this, since it's so bad to like overwrite? Yeah.
Is the reason that the C compiler does it is because we're not supposed to do that?
That is actually exactly the reason. So the justification in the C standard is that accessing arrays out of bounds is undefined behavior. And the rule for C compilers is, well, that's on you, the user. So if you use this in an undefined way, then we have no obligation to compile that in any correct way. So what compilers do for efficiency is not bother checking that. Instead, just generating the same code you would generate as if this were in bounds. So you can imagine a compiler, generating code or trying to check whether this is in bounds. You could try to write a compiler to do that, or you could insert additional code, but that would mean like every single array access takes 3 or 4 instructions with a potential branch instead of just like one instruction. Yeah.
So why is it in C that if you try to like go to an array name that's outside of the actual array, it will just take you to the next I can't remember the name, but the next basically memory address, that's the name.
Yeah, it makes memory address.
Something like Python or Java, if you try to go outside the index, it'll yell at you.
Yeah, so that's because, so the question is, why can you do array out of bounds? So in C, this array access gets translated into pretty straightforward C code. It's going to be something like, if I'm assigning to it, then we already saw in assembly how to do something like this. It's going to be, it's got to actually compute the offset. So this is, I'm going to translate this into C, but it basically turns into array plus I times whatever the size of the data type is. So if this is like a 32-bit int, gets translated into this address calculation and then dereferenced. I can't remember my C anymore. It gets dereferenced. So dereference on the left or the right? I can't remember anymore. It gets dereferenced and then assigned. So it gets translated into this operation. If you wanted to make sure it wasn't out of bounds, you'd need a bunch of things. You need to keep track of the bounds of the array. You'd have to translate it into something like, if I is greater than or equal to 0 and I is less than 5, then do this part, do the actual assignment, else do something else like crash or halt or report an error or don't do it. So it's just more code. You could do this in C compilers, but I think C programmers and C developers, this would kind of dramatically alter the performance of your software. In Java, they do this. They do insert these dynamic bounds checks. They also have an error reporting system so that when it does happen, you can handle that. You can write code to handle those errors. In Python, it's not a compiled language. So their array data structures contain the bounds, and then they also do this error checking as well at runtime. So the difference is something like a choice in how you implement these languages. In C, the choice is, if you don't have undefined behavior, the compiler has no obligation to do anything expected because it's not defined. So the compilers will just do the easy translation and efficient translation, assuming that the developer does not misuse the language. Unfortunately, developers did accidentally, subtly misuse the language, and it wasn't really much in cases like this. It had to do with string processing, where strings are effectively arrays, but it's easy to not think about their bounds, because if you're reading strings from the user and you're not providing enough space for those user inputs, it's very easy to use string functions that just overwrite bounds. Okay, so other questions on this concept where arrays are just allocated in memory contiguously? In most C compilers, or in all C compilers, we can't actually determine at compile time in general whether an array access is out of bounds. And most C compilers make the choice for efficiency to always translate all array accesses the same way, regardless of whether they're out of bounds or not, just trusting that the developer will make sure they don't make out of bounds accesses. And so what that leads to when we have stack allocated arrays is that we can now overwrite the return address. All right, questions on this, thoughts? So that's going to lead us to this security exploit. But before that, let's take attendance. All right, so let's do a stack smashing attack. So this is based on the tutorial that I just took from the internet, and I just adapted for class. So credit goes to this blog post. One of the earliest descriptions of this attack is from, decades ago, in this classic kind of hacker magazine, online magazine, Frack. So you can take a look at those if you want to see the history of this. And I made a GitHub repo if you actually want to try to run this attack, so you don't have to do it on your own machine. In these decades, there's been several mitigations against this. So this actual attack is not possible on your machine unless you turn off some protections. I don't recommend doing those, so do this in the Docker machine. But it's like a fun illustration of some of the kind of early attacks, and we can talk about I'll talk briefly about some of the mitigations against these as well. But yeah, let's take a look at the attack. All right, so the kind of basic idea behind this, the kind of classic version of this, is we've got our currently executing stack. The return address is here. We have some array as a local variable. And typically this is due to string operations. So strings are just character arrays, but this is some character array. Here, that's processing some string. And the attacker is allowed to write strings into the system. So for instance, if you have a web server, so I'll just draw a little diagram about like brief kind of intro to network programming. If you remember, in the Unix world, how does I/O work? How do we do I/O for our software? How do we get input to our software? How do we read data? So in your MySH, how did you get the user to give you data to your program? How did you get input to the program? What's that? Standard in, right? Standard in. It was just a file. So network programming works the same way. So if I have a web server here, let's say I have the Apache web server, for your program, your MySH program, you just used standard in, and then you used like read and write, right? It was a file, so you just did read and write. If you have a web server, it works the same way. You just read effectively from a file. Now this file is called a socket, and there is the Unix style sockets. Network programming did not win out. The TCP/IP stack, the BSD Unix style, went out, but it has effectively the same instructions. It has read and write, and you treat it just like a file, just like a stream of bytes. But instead of this coming from the local machine, this comes from a remote machine over the internet, over a network. So for the application doesn't really care whether this comes from a remote machine, from a local machine, from the console. It's just reading and writing data. So when you're sending a request to a web server, like you say, get, like, you connect to Google or something, and you say, give me the HTML file, your browser is literally sending something like a text chat that just sends this to via the other machine. It sends it to this software, and the software just says read, and it literally reads this string and then processes it. And then it writes out the actual HTML of that web page, and then your browser lays it out and shows it to you. But under the hood, Apache software is just reading and writing bytes, just like it would for a local file or for a keyboard input on a local machine. So it's just doing text processing. It's just processing text. Now, if you have one of these strings being stored in a stack allocated variable, and you only allocate 5 spaces for a string, but the attacker can send you thousands of characters in that string, then you just copy that string to your local variable, you can very easily overwrite all of this data on the stack, including the return address. Make sense? So if you just literally do string copy, the string copy function will just copy whatever long string you have, and it'll copy into the stack, overwriting and blowing away the stack frame. So what attackers learn to do is and so that's very easy to just break your program. So when you return from the function, it'll just crash if you put some arbitrary address in there. But what attackers learned that they could do is, instead of writing just an arbitrary address to crash the machine, inside the string that they copy, they put assembly instructions. They put instructions that will actually run correctly. So for instance, you can run the shell program. You translate that into assembly, the code that runs the shell program, and you change the address so that it will point to the code that you just inserted via the string. So you translate that code to a string, because a string is just what? It's just a binary integers. So you translate it to a string, and then try to put an address here that will jump into the code that you just sent in your string. That sort of makes sense. So that's the basic attack. In our version of the attack, we're going to insert the code we want to run via the environment. So we're not going to put it on the stack. Instead, if this is the stack up here, and this is like the heap and the other, actually I think it's stored on the heap. So this is the stack up here, and this is the other data of the program, heap and global data. We're going to use the bash environment to insert code that we'll call a shell into our program's memory space. And then we're going to try to change the return address, overwrite the return address so it points to that code. So that when the function exits, it'll jump to this code, this assembly code that will execute a shell for us. And that will give us root privileges on our machine for specific programs. It'll allow us to run as shell, running as another user. All right, so that's the basic idea. I know it's like very high level, very diagrammatic. So a couple things to note here is that the Unix environment provides an environment, or the Unix programming environment gives these environment variables to each program. Did we talk about this before, like the path environment? We talked about it a little bit when we talked about the Unix world. But there is a set of, basically a database of variables that each program has access to. And this gives you things like path. So the path defines the list of directories where you can find programs to run. This is why I can say ls, even though ls is not in my current directory, my bash program can find it because it has this path environment variable to look through. So this is available, and this is also why when you, I don't have user here. So user's not set there, but on my system, the user environment variable has my username. That's why you could put your Git URL and just put user in there. That's why you were able to do that, because this environment was available to all systems. And it turns out that we didn't talk about it much when we talked about the exec syscalls, but some variations of these system calls also take an environment map, a map of the environment variables. And so whenever a new program is executed, the program is given, the arguments are given, and this environment is also given to the executing program. So this is just the Unix system. This is the Unix programming system. This information is put in memory for each running process in the program. And it enables all these features like, the path, having the user name available, the shell available. Okay. Another aspect of Unix to understand for this is there is this ability of programs to run as the root user. So let's take a look at bin here, or maybe it's sbin. I think I forgot to maintain an example of this. So there are programs that need to run with root privileges to do things like access privileged data or access privileged I/O devices. And in the so there's a Unix syscall called setUID, which will change the user that you're running as. And so if the permissions are set for this program, you can change your user to root and run as the privileged root user. So if you have an attack where, if you can attack a program, if you can find one of these Stack Overflow attacks in a program that runs as root, well then you can run any code you want as root. So the attack we're going to see today that was developed in that blog post is we're going to use the stack smashing attack to run a shell, and we're going to attack a program that we created, but a program that has the ability to run as root. You know, historically, if the program was owned by root, you could run as root, but the security model has changed since then, so we have to set a special bit that will allow this, a security bit. But basically, historically, if you had a program owned by root, it was allowed to run as root, and this was necessary for all sorts of like system utilities to run like this. And so if it has one of these overflow vulnerabilities, we can just run because we can run any code we want, we can run any code as root, thereby doing privilege escalation. We can run anything we want as root on that machine. Makes sense, sort of? Questions about this? This is like a super brief intro to like the Unix security stuff, but that's our goal. We're a user on this system, we don't have root access. There are programs that run as root, and if we can induce those programs to run the code we want to run, then we effectively run as root. Okay, and the strategy we're going to use is we're going to insert the code we want to run, into the environment, because that code is going to be put by the system, by exec, into the memory of our running program. And then all that's left to do is to smash the stack, to overwrite the return address so that it points to that code that we put into the environment in our system. Yeah?
So to stop this attack, would you just have to like restrict what programs the user can run? Like,
well, so there is just code that needs to run as root that the user is allowed to run. So you won't be able to stop it that way. So what you can do is you can defend against the stack smashing attack. So make sure that code doesn't run as root. You can also, one thing that was changed in the security model was, where can I find this? So it even like describes it here. So there are some programs that are owned by root. So for instance, LS, all of the utilities are owned by root, because if they're owned by a user, the user can just overwrite it, and then everyone else will be, then everyone else will run that code. So you wouldn't want other people to run code owned by another user. And I think originally it was the case that any code owned by root could call setUID and be run as root. So they changed the, where is this? Yeah, so they changed the permissions model so that if you want a program to allow it to be run, setUID as root, you have to set a special bit on that program. So that was one change. And so we actually have to set this special bit in order to have our setUID call work properly. So that was one way. That's one way to defend against it. This tells you how to like set that bit. But yeah, defending against a stack smashing attack is how you like protect against. You want to make sure that no code that needs to run as root ever has this stack smashing attack to it. So there's lots of ways to defend against a stack smashing attack. So you can make it hard for the developer or the attacker to guess what the return address is, because we have to figure out what the return address is to our code. So you can make that harder. One way to do that is to randomly move the where data is in memory. So for instance, you start the stack at a different address, you place the environment variables in different addresses in memory so that the attacker can't easily figure out what address they have to jump to, even if they can smash the attack. You can add compiler checks that will check whether the stack has been smashed. So one technique is called a stack canary, where they'll put in addition to the stack frame, they'll add a special random number here called a canary. And before they return, they'll check to make sure that this address wasn't overwritten. So it'll be like a hard to guess number or a randomly generated number at runtime. And so if the attacker has indeed smashed the stack, they've overwritten the return address, it means they would have had to probably overwrite the canary as well, potentially. And yeah, that will show that the stack has been smashed, and then the machine will stop. It won't try to run it. There's also another technique called control flow integrity, which makes sure that the returns only go to the functions that called them. So there's a whole suite of techniques for defending against this, and we have to disable some of these techniques in order for this attack to work. But yeah, you just have to basically make sure the code is not vulnerable to that attack. And then there are defense in depth mitigations to make sure that even if it is vulnerable, the attacker can't take advantage of it. All right, any other questions, thoughts on this? So you don't have to worry too much about like the specifics of the security model or like, how the environment works or why it's there. I'm just gonna kind of walk you through the pieces of this attack and show you how you can exploit a vulnerable piece of software to actually get root privileges on a system configured in a very specific way. Okay, so let me get the attack description up. So here's our instructions, and here's our system. All right, so we've got this So this is our program that's vulnerable to a stack smashing attack. And we're going to set this program to be owned by the root and also to be allowed to change its user while running to be the root. So here's what this program does. It just prints out a statement and then calls this function, vuln, which defines an 80-byte character array and then just reads from the user 400 bytes. So a very, very blatant overread or overwrite of this buffer. And then says, okay, I've read this many bytes, tries to say you haven't successfully attacked, and then it returns. So you can see here that already it's reading up to 400 bytes. So this is not what vulnerable code normally looks like. Normally it's string operations, but this is just a very fabricated example of a stack smashing attack. Questions on this code? So we've defined an 80-byte array, and we're reading in 400 bytes to that array. It's stack allocated, so if we indeed read in more than 80 bytes, it's going to start blowing away parts of our stack frame, including the return address. Okay, so I have code to compile this. I've already run Docker. All right, and all this, so I'm not a security exploit expert. I largely took this from the blog and my own knowledge of how the compiler works. But there's a suite of tools that will help us perform this attack. So the first thing we do is we just create this file that has 400 A's in it, 400 letter A's. And this is what we're going to read into our program. So remember, our program can read in 400 characters to an 80-byte array. So let's just see what happens to our machine, or to our stack when we do this. All right, so I'm going to use debugger for this. This is just going to pause when we enter the vulnerable function, and R just runs the program. So I'm going to run the program, passing in these 400 characters as input. So you can already see that this is what our stack. So this is a toolkit called PEDA that will provides a kind of a wrapper on a debugger that will show you all sorts of interesting parts of the machine state. So we did this diagrammatically in class, but you can see the state of all the registers here, including the instruction pointer. You can see the state of the stack, or sorry, this is the code, and you can see the state of the stack. So if we go into our code here, line 13 is here at the end of our function. So this is after we've read in all the code, just before we return. So you can see our stack just has the letter A in it over and over and over and over again. Why is that? Why does our stack have letter A in it over and over and over again? Because we read 400 bytes into an 80-character buffer, and that overwrote everything, including our return address. And we can actually see so we can actually see that our return address, our saved return address, so this is what the return address is going to be, is just, I think that's the letter A. So if we look at ASCII, capital A is 41. So our return address, so this saved RIP, this is the return address from the stack. You can see it's already been overwritten with the letter A. So we've already smashed the stack. We've already smashed it by overwriting the return address. So how can we exploit this to actually run the code that we want? So if we continue running, what's going to happen? It's going to try to branch to that address, which is 41, 41, 41. There's nothing to run there. That's like the machine will try to run it, but we get this sig fault because it's in an address space that our process doesn't have access to. So we get a seg fault when we try to run this program. Okay, so how do we take advantage of this program? So the first thing we need to do is we need to figure out where in that sequence of 400 characters where the return address actually is. So we could probably compute that by sitting down and thinking about how big the stack frame is, where the address is from there. But this toolkit provides us an automated way to do this. So we can create this special pattern file. I don't exactly know how this works, but it basically creates a unique pattern for like each distance from our array in our array, so that we just look at what the return address is, and that will allow us to figure out what the offset is of the return address. So if we run our program with this pattern file, the pattern file, instead of just all A's, it's going to be a sequence that allows us to figure out the offset. And we look at our stack pointer now. Our stack is filled with this data from our pattern.txt file. So one thing to notice here is that every time we run this program, actually I didn't. I turned it back on. Still not changing. So I shut this off already, but there's this technique that will randomize the layout of memory of your process, and I had this turned off, but if you have this on, it'll be hard to guess the address of stuff in memory because it'll be hard to guess that address because the layout of your memory is randomized by the loader, by the architect, by the system itself. If we turn that off, then that layout, that defense is no longer there, and so we'll be able to know for every execution of your program exactly which address everything in that memory space of your process is. Okay, but anyway, so this is so yeah, created this pattern already. Run the program. So this will show us the pattern that's in our that this will help us. Sorry, this will help us find where our where what the offset of our return address is in our program. So all right, so we run this program with this pattern. We look at the value of the memory in our stack, and then pass this value to this algorithm that will tell us what the offset was of our return address. So we've discovered that the return address was 104 bytes from the beginning of our array doing this. So this is using some fancy techniques that this exploitation toolkit has. But then we can take this knowledge, this offset of 104, and we can target overwriting the return address. So this is going to generate 104 A's, and then overwrite the return address with the letter B. So hex 42 is the letter B, and then overwrite the rest with C. So diagrammatically, what this is going to do is, if our array is down here and our return address is here, our return address has an offset of 104 from the buffer. So this is going to write A into everything before the return address. It's going to overwrite the return address with B, and then everything after the return address is going to be overwritten with C. So before we just overwrote everything with A, and we use this tools that we have in our toolkit in order to identify what offset the return address is from our from buff. And so now we're going to test this out by overwriting the return address with B and everything else around it with different letters. So that way, when we go to inspect our instruction pointer after the stack has been smashed, we'll be able to see that it's the letter B. Okay, so now we have this file that has 104 A's, followed by B's, followed by C's. So let's run our program using this file as input. And you'll see that our instruction pointer is now hex 42, which is the letter B. So we've successfully blown away our return address with a custom number that we defined. So we know exactly what offset to use in order to blow away the return address specifically. Okay, so we've been able to smash the stack, and now we have control over what the return address value is. So our next step is just to take that control we have over the return address and point it to some code that we want to run. And this is where we're going to use the environment variables in order to insert that code into memory. So to do that, we're going to take some pre-existing shell code. So there is this actually website that gives you examples of shell code. So the shell code just gives you examples of different syscalls for executing a shell translated into assembly for different languages. So this is this program that calls setuid0, which says run this program as root, and then it just calls execve on the shell. So hopefully this one is familiar. You use this in class to run processes. So we're going to call exec, which is going to replace our current process with the shell process. And before we do that, we're going to call setuid in order to run as root. And this is the assembly translation of that program. And this is the encoding of that assembly as a string in C. So it's just translating this to its actual machine code binary, and then encoding that machine code binary as a C string. If that sort of makes sense. So we're going to take that C string, which is here, and we're going to save it as a environment variable. So now if we take a look at our set of environment variables, we have this new environment variable called pwn, PWN, and it's going to be set to this C string that contains our shell code, already translated to machine code. So because this environment variable, these environment variables and their values are stored in memory, they're put in memory by the kernel's loader, this is going to be in the same memory space that our stack is and our code is for our class, for our program. So if we can change that return address to be the address that this code starts at, then we're going to run our shellcode. We're going to run as root, change ourselves to root, and then run the shellcode. Yeah. Well, this is like a hacker term for own. I think it's just a misspelling of own. Actually, it comes from the gamer world, I think. But it's like pwn. It means you've been owned or you've been pwned. That's the, I think, etymology of that term. Yeah. So that's how we're going to get it into memory. And so there's these other utilities in here that this blog post gave for figuring out the address of this environment variable's value. So get event is how you get the environment variable itself, and then there's just some calculation to figure out what the address of that code in memory is. So if we run this code, this is going to tell us where in memory that environment variable is. So there's just some other instructions here that allow you to see, it'll disassemble that shellcode. So if we had the address space randomization turned off, you'll see when I run this program that gets the address of this environment variable, you see the address changes every time we run it. That would make it impossible to do this attack because we can't predict what the address is to overwrite a return address. So I turn off this defense called ASLR, address space layout randomization. I turn that off, and now the address is the same every time you run the program. So the loader always puts the program in the same place, always puts the environment in the same place every time we run. So this address is the address we want to overwrite the return address with. This is the address of the shell code in memory. This is the address of that assembled setuid and exec program. So now we know the address of it, and so all we have to do is now we have control over this address. We just have to overwrite that return address with the address of our shell code. So here's our file that will generate the exploit. So this is just, we'll generate a file that has 104 A's, and then at the return address spot, it will insert that address that we now know is the address of our shellcode. So I'll run this. Here's our exploit file. Okay, so here's our program. Here's our vulnerable program. So notice that it is owned by root, and this S in the place of where the execute permission would normally be says we're allowed to use setuid for this program. So there's all sorts of defenses against this nowadays. So most software, even it has a stack smashing vulnerability, would not actually let you run as root. So we've set everything up to allow this attack to take place. So let's see if it actually works. Okay, so we've run this program. So remember, this is what the program does. So it reads in 400 bytes. We passed in the exploit text. That exploit text just replaced the return address with the address of our shellcode, and then continued to pipe input from the user to the program. So it ran this code here. It printed out the number of bytes, printed out the buffer. it printed out this string saying no shell for you, but then when it returned, instead of returning to main, it returned to our shellcode, returned to that address that we put in to our exploit.txt. And now I'm actually running on this system as root. As you can tell with the whoami command. Whoami command just says what our current user is. So now we're actually running as root. We can do things like touch files only as root in places that only the root can touch. So you can see I've made a new file that only the root can do. So if I tried to do this as a normal user, permission denied because I'm not that user. If I tried to run this program without using my exploit code, yeah, it says no shell for you and immediately exits. But if I pass in this code that will, or if I pass in this input that will replace the return address with the address of my shell code in memory in the environment variable, well, it doesn't exit. Instead, it returns to that shell code and then calls exec. Remember, exec just replaces the current process with whatever process you gave it, or whichever program you gave it, which is shell. And voila, now I'm the root user on this machine. Okay, so that's the attack. Questions on this? Thoughts on this? Anyone seen this attack before? Has anyone seen this attack smashing before? Some people might see it. So if you're part of like HackUCF or you're interested in this stuff, you may have seen this. All right, so that's the attack. So the reason that I show this is because it's extremely relevant to how we wrote the compiler in our class. So and how C compilers work in practice. So the reason that attackers could do this exploitation is because they had, close knowledge of how the compiler implements functions at runtime. And because this is like a standard for all, at least Unix, most operating systems have a standard where they implement functions in this way. This attack created a lot of vulnerabilities, but it depends on this knowledge of how the compiler works. Okay, if you have any other interest in this, so there is a club here, HackUCF, which gives these kinds of tutorials, I think, regularly. You can check out the original, or one of the original papers describing this. Check out the blog post. You can check out my link if you actually want to run this on your own machine. And there's also a good website, pwn.college, which goes through software exploitation, if you're interested in this kind of software exploitation. But yeah, other questions? All right. So that's it for the main content of this class. So I'll see you guys next week if you're able to come. It'll be recorded. It'll be the final exam review, and then in 2 weeks we'll have the exam. I have a office hour schedule for that week. I'll have extra office hours for after your submission, and if you have questions about your exam. But otherwise, I'll see you all next week. Bye, everybody.